This video covers hidden Markov models. I'll provide some background and a formal definition, along with working through a case example. Just like with finite state automata, transitions in hidden Markov models can be represented using transition tables, so I'll also show an example of that. Finally, I'll introduce some fundamental HMM tasks that we'll cover in more detail later in this module. In a nutshell, hidden Markov models are probabilistic generative models for sequences. They model the likelihood of different sequences occurring based on an underlying set of hidden states. These are states that the model can be in, but that are not observed directly. For a lot of NLP tasks, people are interested in assigning categorical labels to segments of text, with each of those segments being considered as independent units. Spam detection is a good example of this. You take an entire email, extract some features from it, and then use those features to decide whether the email is spam or not. However, this assumption that each individual decision is independent of all of the other decisions that need to be made doesn't really hold in a lot of NLP problems. Often, NLP problems instead involve a bunch of interconnected decisions. So to solve them, we need to make use of different learning and inference techniques. Sequence labeling is one of these strategies. In sequence labeling, rather than assigning labels in isolation, you assign labels based at least partially on other labels in the sequence. A classic use case for this is part of speech tagging, which we'll talk about in more detail later this semester. Part of speech tagging is where you assign part of speech labels, so things like noun, verb, adjective, and so forth, to words in a sequence of text. A lot of times, words can have multiple valid part of speech labels depending on how they're used. For example, the word break could be used as a noun or as a verb. So to decide which part of speech label should be assigned to a word in the context of its current sentence, it can be very useful to see what part of speech labels have been assigned to the other words around it. In the case on this slide, seeing a determiner, which is a word like a or the, right before the word break, provides a really strong clue that it's being used as a noun rather than as a verb. On the other hand, seeing a noun right before the word suggests that the word break might be being used as a verb instead. Other NLP tasks that can benefit from sequence labeling include named entity recognition, which is where you identify specific instances of different types of entities, for example, organizations or people, and semantic role labeling, which is where you identify the role that different words are playing in a sentence. We're focusing on probabilistic sequence models. So that means we're focusing on statistical models that make their decisions based on multiple interdependent classifications. There are two classic classification models for doing this, hidden Markov models and conditional random fields, and in this video we'll be covering the former. Before we talk about hidden Markov models specifically, we can backtrace a little bit and talk about Markov models in general. Markov models are just regular finite state automata plus probabilistic state transitions. So rather than saying that state Q1 transitions to Q2, we can say that Q1 transitions to Q2 70% of the time. Markov models are based on the Markov property, which basically says that the next state of a model depends on the current state and only the current state. Sometimes you'll also see Markov models being referred to as Markov chains. Here's an example of a Markov model to illustrate. Note that it looks almost exactly like a finite state model, just with these added probabilities. To determine the probability of an entire sequence occurring in a Markov model, you can just multiply the individual transition probabilities for that path. For example, if we want to find the probability of the sequence Q3, Q2, Q1, Q4 occurring in the present model, we would multiply the probability of transitioning from Q0, the start state, to Q3, times the probability of transitioning from Q3 to Q2, times the probability of transitioning from Q2 to Q1, times the probability of transitioning from Q1 to Q4. That'd be 0.2 times 0.1 times 0.2 times 0.3 for a product of 0.0012. Hidden Markov models assume that on top of what you saw in the previous example, the states themselves are hidden. So you can't directly observe the sequence of states. Instead, you make observations of what comes out of the states. But you can assume that there are probabilistic transitions from one state to another, and you can also assume that observations are probabilistically generated from those states. So here's our same Markov model as before, but we've added some extra information. We now have probabilistic observations. So we know, for example, the probability of observing an X given that we're in Q1, the probability of observing a Y given that we're in Q2, and so forth. HMMs can more formally be defined as having the following components: a set of states, Q, a transition probability matrix, A. This is a matrix of the probabilities of moving from one state to another. A sequence of observations, O. The observations all belong to a fixed vocabulary. So if our vocabulary contains 3 words, dog, cat, and reindeer, then we can't suddenly observe unicorn. A sequence of observation likelihoods, B. These likelihoods are also sometimes called emission probabilities. Each of these likelihoods expresses the probability that a given observation was generated from a given state. And then finally, a start and final state, and the associated transition probabilities out of the start state and into the final state. So then, if we take the definitions from the previous slide and go ahead and label our sample hidden Markov model, we can see these terms in practice. We have our sequence of observation likelihoods B here, and our transition probabilities here. We'd already labeled our states previously. If we take the model in the previous slide, shown here on the left, we can also go ahead and create a transition matrix for it. For this transition matrix, our rows correspond to the state we're currently in, and our columns correspond to the state we're going to next. The values are the transition probabilities from one state to another. There are plenty of practical applications of HMMs, and one that illustrates the different components really nicely is text generation. To generate text using an HMM, you begin in the start state, and then for as many observations as you want, you randomly select a new state based on the transition distribution for the current state, and then randomly select an observation from the new state that you moved into based on the observation distribution for that state. You can generalize this to sequences of whatever you want, but I'll work through an example of generating text using an HMM next. So we'll start off in our start state, Q0. We have some transition probabilities specified here, and we also have some observation likelihoods. So for example, in Q1, we observe that we have a 0.3 likelihood of selecting the word my, but only a 0.1 likelihood of selecting the word her. There are several states that we can transition to from Q0, we can transition to Q1 with a probability of 0.7, Q2 with a probability of 0.1, and Q3 with a probability of 0.2. We select the next state randomly according to this distribution. Basically, this means that if we had a big bucket to fill with possible options, we might put Q1 as a possibility 70 times, Q2 as a possibility 10 times, and Q3 as a possibility 20 times. So we're more likely to end up pulling out Q1, but we're not guaranteed to. In this case, we do end up pulling out Q1, so we transition into that state. Now, once we're there, we can generate one of 4 possible words. Again, there are probabilities associated with these. We'll select one randomly, but we're likelier to select the my or Mina's than we are to select her. We end up randomly selecting my, so we have our first observation. Next, we need to decide where to go next. We can stay in the same state, move into Q2, move into Q3, or move all the way into Q4. We'll select randomly again, but it looks like it's most likely that we'll move into Q2. And we end up being correct. So now we're in Q2, and we have 4 new options of text to generate: dog, cat, lizard, and unicorn. Again, we have a probability distribution, and we'll select randomly according to this distribution. We end up selecting unicorn, so now we have our second observation. So far our generated text is my unicorn. There are 3 transitions available to us now. We can transition back to Q1, onward to Q3, or all the way to Q4. Again, we randomly select according to this distribution. We end up selecting Q3 as our next state, so we transition into that state. There are only 3 words we can generate from this state: laughed, ate, and slept. We'll select one randomly according to the observation likelihood distribution. And we end up generating the word laughed. From Q3, we can transition back to Q1, back to Q2, right back to the same state, or onward to Q4. We randomly select one of those states according to the distribution, and we end up reaching our final state. So our generated text is the sequence "my unicorn laughed." There are 3 fundamental problems that can be solved using HMMs, and there are different algorithms for tackling all of them. The first problem is determining how likely a given observation sequence is to occur. The second is determining the best sequence of hidden states for a given sequence. And the third is determining the transition probabilities and observation likelihoods that best fit the observation sequence and HMM states. We'll discuss those problems in more detail in the remainder of this module before turning our attention to language modeling.